Hi guys, good to have you. Welcome. I'm happy to see that the sun is out, the weather's warming up. It's all going to be all right. Okay, so I'm going to teach you today about some of the questions that you might have about, well, this common approach for estimation. Um, there are some parameters in here that we're going to have to be able to figure out, like what's our prior if we don't know anything. So in order to start estimating, you have to have some prior, and that prior has a mean. That's your parameter that you're trying to estimate, the mean of that parameter. You have some uncertainty about that mean. And that uncertainty, if you don't know anything, that's going to be infinite. That's going to be a problem. So I introduced this from the perspective of regression. And so here's what we have. We have our mean value, and we have our, yeah. Oh, it's not on? Oh, okay. I'm sorry. I don't know why. It's there? Okay. Wonderful. Sorry about that. Okay, so look, but when we want to start estimating, at the beginning, we have to have a prior belief about what is it that we're estimating, and that belief is always a distribution. It has a mean and it has a variance. The variance is called uncertainty. The mean is, in this case, W hat. That's what we're trying to estimate. So I want to tell you about how do we get that initial value, and why is it important to have that some initial value? Well, because in order for you to get the common gain, what is the common gain? Look at the equation that describes how your measurement. So this is your measurement equation. This is how what you measure depends on the parameters and the input x that you get. So the common gain is a relationship between the uncertainty in that measurement. So what is the uncertainty in that measurement? In this case, it is the variance of that equation. So that's x transpose variance of w, which is p of n minus 1 x plus variance of epsilon, which is sigma squared, the inverse of that. So you're going to divide by the variance of what it is that you're measuring, times the uncertainty that you have of your estimate itself. So that's a p of n minus 1. And to make this, if you look at the parameters, the size of these variables, this is going to make sense. So for example, if I need to update w hat with my prior plus k times y minus y hat. Y hat is going to be x transpose w hat n minus 1. So this is y hat. This is what I estimated on that trial. This is what I measured. And so w is some vector. Let's call it m by 1. So k is an m by 1. And y in this case is a scalar. So let's look at the way it turned out. So this is an m by 1. This quantity here, this quantity here is a scalar. And then I have p. What's the size of p? So p is the variance of w. W is an m by 1. So what is p? Yes, it's m by m. And x is my state. X is the size of w, right? So that's an m by 1. Yeah. So you see that works out. What I wrote down. The dimensions work out. Okay. So but that's how we're gonna update our parameter. And then I have my posterior uncertainty, which was depends on my prior uncertainty. So this is my posterior. So after I get my data and after I learn, I update what my uncertainty is, and I update my parameter. I update W, and I update my parameter estimate of the variance of that parameter. That uncertainty, this is the posterior uncertainty, is going to depend on the prior uncertainty, and it's going to go lower. It's going to become smaller because I just got data. So my uncertainty about what I know gets reduced. Okay, so um, this is tells you the posterior answer, and then after you get the data point, now you have to have a next trial at Wn plus, sorry, at n plus 1. What is your prior? So I had some prior. I learned, I updated, I formed a posterior, and what is my next prior going to be? If you believe the world isn't changing, well, then you say, well, that's just my posterior in the previous trial. My uncertainty in the next trial is my posterior in my previous trial. So this is my prior in trial n plus 1. This is my posterior in trial n. That's just the model that you have. You believe from time n to time n plus 1, the world didn't change. Now, if you believe that the world is changing, then you have a model that says actually from time n to n plus 1, things are not constant. So there you have your model is W of n plus 1 is W of n, maybe times A, plus some noise. And this noise has some variance. Let's call it Q. In that scenario, then my posterior belief is going to affect my prior on the next trial. So my next trial, W of n plus 1 given n, is going to be A times my posterior in my previous one. So this was my posterior in trial n. This is my prior in n plus 1. Similarly, my prior in n plus 1 is now going to be the variance of that equation. So that's going to be A times P of n given n, A transpose plus Q. So if you believe that the world isn't changing, if this is your model, if W of n plus 1 is equal to W of n, then that's how you update your states. If you believe that this is the model, that it does change, then this is how your posterior is going to affect the prior on the next trial. This is how your uncertainty is going to affect the trial on the next trial. So this is with respect to this parameter W in this linear estimation. Now, in application of this, we're much more interested in dynamical systems. So for example, you have some state X. So now not W, X is what I'm interested in. Here, it's equal to something like this. So this is now my linear system. I give it some input U, it has some hidden state X, and it's going to change when I give it this input U. Now I can't measure X, I measure Y, and that's related to X plus some noise. And epsilon X has some noise, and epsilon Y has some noise. So now what I'm trying to estimate is X. And I'm going to have some mean about my estimate. That's going to be my prior, X hat of n given n minus 1. And it's going to have a variance. So this is my belief, prior belief. It is a normal with some mean and some variance. X is what I'm trying to estimate. Okay, so now let's apply the Kalman framework to this. So the things that you know here, the things that you can measure at every instant in time is that you give some input U and you measure some Y. Now what you want to do is to estimate X. X is what you're interested in. You want to have an X hat. So tell me the internal state of this rocket, of this process, of, if we're applying it to neural recording from the brain, X hat would be, what is the monkey or the human is trying to do? What is they want to move the cursor? What is the position velocity of this cursor, given that we measure some neural activity Y? Okay. So let's do our Kalman filter for this. All right. So this is our dynamical system. Okay. So I begin with a prior, and that my prior has this mean and has this variance about the state. So X is what I'm trying to estimate. I believe it has some mean, that's X hat, and it has some variance about it, P. And it's a normal distribution because all the noises in my system are Gaussian. So I begin with some prior before I see any data, and I'm going to call that X hat of 1 given 0 and P of 1 given 0. This is my initial prior. I have to start with that. Now, I'm going to show you that we can try to guess what this uncertainty should look like, and I'll show you how we can get that. But right now, I don't know what that is. I don't know what is my initial uncertainty because I haven't seen any data. I just don't know anything about the system. So, but maybe I say X hat is 0 and P is infinity, maybe. But I have some prior. Then what I do is that I make a measurement, I make a guess, and then I update my belief based on what I measured minus what I estimated. What is my estimate? What's Y hat? What should I subtract Y of N out of? So look, I always am comparing what I predicted with what I observed. So what am I predicting at trial N? What's my prior belief about what I should measure? It is the mean of this equation. Y hat is the expected value of this equation. So what's the expected value of that equation? It is C X hat of N minus 1, because that was my prior belief. X hat of N given N minus 1 is what I believe the state of the system to be. So at trial N, I multiply that by the matrix C, and that's Y hat. That's my belief about what I should be measuring. This is Y hat. Questions? Does that make sense? Yeah.
Are you adding or are you multiplying?
K of N, multiplying. So, oh, I'm sorry. Sorry. Yeah. Okay. Any questions about this? So I'm always updating my belief based on what I observe, Y, and what I predicted, Y hat. What is Y hat? Y hat is the expected value of the observation equation. It's the expected value. Y hat is the expected value of this equation. And the expected value of this equation is C times the expected value of X. Well, expected value of X is just the mean of X. X hat of N given N minus 1. Expected value of epsilon Y is 0 because this is a 0 mean Gaussian noise. So this is Y hat, C X hat of N given N minus 1. So I update my belief based on K. Now, what is K? Well, it's going to have two terms in it. First, it's going to have this term that is the inverse of the noise in my measurement. So what is the noise in my measurement? It is C times the variance of X. That's P of N given N minus 1 times C transpose plus the variance of epsilon Y. That's R. There's an inverse in front of that. And now this is going to multiply by my uncertainty, and there's going to be a C transpose here. So let's see if this works out. So K here, what's the size of K? Well, if X is, let's say, N by 1, K is an N by 1. This is an N by 1. And if Y is an M by 1, oops, sorry. So K is going to have to be N by M because Y is an M by 1. So K is a matrix now. So K is an N by M. P is the variance of X. What's the size of P? N by N. So variance is always a square symmetric matrix, right? So if N is a vector of size N, its variance is an N by N. All right. C transpose. So what's the size of C? if X is an n by 1, what is the size of C? Good, m by n. So this is an n by m. So far, so good. Okay, what's the variance of, what's this term here? What's the size of this term? Well, it better be R. R is epsilon y, variance of y. So this better be an m by m. So it works out. So that's K. Okay, then I have my posterior uncertainty. Okay, so now I have my Kalman gain, I have my posterior uncertainty. Now what I need to know is what is going to be my prior belief on the next trial. So in trial n plus 1, what's going to be my X and what's going to be my prior belief, what's going to be my mean, and what's going to be the variance of that mean. So the mean of my belief is X hat. So X hat of n plus 1 given n. This is the mean of it, and I have some variance. This is the prior on the next trial. So what is going to be X hat of n plus 1 given n? Well, let's look at our equation. Look at this equation here. This tells you how n plus 1 depends on n. And the expected value of this equation is what's going to go into my equation. So this is going to be A times the expected value of X, that's my posterior, plus B times U of n, and the expected value of the epsilon, the noise term, is just 0. So this is what I expect the state of the system to be at time point n plus 1. After I made my measurement at time point n, this is what I expect it to be at time point n plus 1. My posterior uncertainty, well, that's also comes from this equation, the variance of this equation. So let's see what the variance of this equation is. It is A times P of n given n, A transpose, that's the first term. B times U is not a random variable, so it doesn't do anything. Then I have this epsilon X at the end of that equation. It has variance Q. So that's how I update my posterior uncertainty so that it becomes the prior on the next trial. So this is prior on trial n plus 1. Okay, so let me stop, see if I made any sense. Yeah.
You were assuming when we calculate the variance of n plus 1, there's independence for each noise within each trial.
Right. It's a Markov model. Very good. There's no covariance between the noise between this second and the previous second. Okay, questions? All right. So how do I get this prior on my very first data point? So how do I get this? How do I get, look, if I don't know this, look, I need to know something about my uncertainty, because how can I compute my common gain? Because I need to know my uncertainty before I can compute my common gain. And if you start the process, and if you don't know anything about what the state of the system is, your uncertainty is infinity. Well, you can't find, you can't put infinity there. So how are you going to find that? But there's a relationship between this and maximum likelihood. So remember, in maximum likelihood, we didn't have a prior. We just found the maximum likelihood without having a prior. And it turns out that it's effectively the way to find that initial uncertainty to put in there is to use the concept of maximum likelihood. And I'm going to show you that we can get the initial uncertainty and initial mean from it. So, okay, so the question that I want to now ask is that how do I find, how do I start this process? Meaning, how do I find P of 1 given 0? How do I, if I don't know anything, I can't put infinity there. So, which is also, this is how do I find my very first K of 1, my first common gain? Because if I know the first K, if I know the first P, I can compute everything from then on. But how do I get the very first one? That's what I want to show you. So why do I say that? Look at these equations here. So I began by saying that I have X, some X hat at time point 1 given 0. I just have a prior belief about the state of the system, maybe because I think the rocket is sitting on the, on the launch pad, and I have some uncertainty about that state. If I knew those two things, then recursively, I could compute K and I could compute P. I could just compute that from now to the end of time if I knew that initial conditions. Because look, K doesn't depend on X, P doesn't depend on K. Sorry, but P doesn't depend on X, K doesn't depend on X. So yeah, as long as I have some initial condition, P, I can compute this forever. But how do I get that first point? And that's what I want to show you. All right. So so here's our equation, right? So we have K of n and just to remind you, this quantity is the variance of y given x. So this is your noise. This is your uncertainty in what you're measuring. This is your uncertainty about what you believe. This is the variance of x. And then I have the posterior uncertainty. Okay, so now my question is, how do I find my first P? So let's multiply this out. And put in K. So I'm just going to put the equation for K inside of this equation. All right. So the way to solve this problem of how do I find that first uncertainty is to think about this. Well, if my uncertainty is infinite, if I really don't know anything about this, if it's really infinite, then if I had some way to represent uncertainty, not in terms of P, but in terms of inverse of P, then that would go to 0, right? So I don't want to put infinity in my equation. I want to put the inverse of P in there. I don't want to have P. I want to have an equation that has the inverse of P. In that case, then I can put infinity there and say, okay, that just goes to 0. You see, that's the idea. So this idea is the heart of this approach that I want to show you. So it relies on something called the matrix inversion lemma. Okay, so why do we need an inverse? Because we want to take something that is nearly infinite and we want to get rid of it. So we want to find a way to represent our task with just an inverse. And here's the lemma. So if you have some matrix X, Y, and Z, three matrices, X, Y, and Z. If you had some subtraction of them, Z minus X, Y inverse, X transpose inverse, if you had that, this matrix inversion lemma says that this is equal to the following quantity. So here, X, Y, and Z are just some matrices. So matrix inversion lemma says, look, if you have this quantity inverted is equal to this quantity. All right, so why is this useful for us? Well, because look at what I just wrote regarding posterior uncertainty. So look, this quantity here is this quantity is this quantity is this, and so forth. So what I'm saying is that in this equation, z minus 1 is minus the prior uncertainty, x is C transpose, and Y is R. So let's just replace that with, with what I have. So then that says P of n given n is minus Z inverse plus Z inverse times X times X transpose minus Z. I just put in the what I have in this equation. I just replaced this with X, Y, and Z as I've written it here. So if I do that, then what happens is that look, then what this says is that the posterior uncertainty is equal to this, which must be equal to this quantity here. So that is which is equal to C transpose R minus 1C plus the inverse. Okay, so this is look, this is what I wanted. I wanted the posterior uncertainty to be related to the prior uncertainty inverted. Why? Because my prior uncertainty is I don't know anything, so it's infinite. So now if I have something that's raised to a minus 1, I can get rid of it. So let's simplify this equation. I get just invert the left side. I get all right. Very good. So and I can get rid of these parentheses. Bless you. Okay, so why was this useful? Because look, if my prior uncertainty P of 1 given 0 is infinite, then what this says is that if I were to take a data point and update my uncertainty, then P of n given n minus 1 is just going to be C transpose R minus 1C, which means P of n given n is the inverse of this. Okay, that's great. So if I have no knowledge about the parameter of my problem, I can assume an infinite uncertainty and still compute my posterior uncertainty. But look at this equation here, C transpose R minus 1C inverted. This is, if you remember when we were doing maximum likelihood, when we were trying to find the how to combine two pieces of information based on their variance, this was the posterior variance that we get after combining two pieces of information, equally weighted by the noise in them. And so what this is saying is that if you don't have any better pieces of information than just assuming, you know, my prior is infinite, you can um, you can still proceed. So what about the common gain? Because remember, in order for me to proceed, I need to not just have a way to compute the posterior uncertainty. I also need to have a way to compute the common gain. So what is going to be the common gain? So my equation for the common gain was this. This is how I was going to compute k of n at any given instant in time. I could compute what the common gain should be to learn from error. But this is in terms of my prior uncertainty. Can I write it in terms of my posterior uncertainty? Because I don't have a prior uncertainty, it's infinite. So let's try this. Let's multiply the left and right side by the inverse of that equation here. So that becomes the following. And I can multiply it by R. And this term here, this is the posterior uncertainty. Okay, so what this says is that if you know nothing about your task, you can begin with the following estimate of uncertainty. You can just say my uncertainty is going to be C transpose R minus 1 C inverse, because that's assuming that you know nothing. And then you can also compute your common gain based on the estimate of the posterior uncertainty that you have. So you can begin the task using these initial conditions. If your uncertainty to begin with is infinite, you can still compute the uncertainties that you need to proceed. Okay, so let me summarize what I did. So to start with our process, we wanted to know how do we begin by finding P10 and K10. What I did is that I showed you that if you can write the posterior uncertainty in terms of the inverse of the prior uncertainty, then if your prior uncertainty is infinite, this goes away. You have a term that you can use. This can become your prior uncertainty. So you begin by assuming P10 is this. You just say, I'm going to assume that that's my prior uncertainty. That's how I'm going to begin. And you can still compute the Kalman gain. So this is K1. K1 is P1, 1, C transpose R minus 1. Okay, let me stop to see if you have questions. All right, so what's the relationship between this and maximum likelihood? Why did I say that having no knowledge, no prior belief is equivalent to being maximum likelihood? Because look, K1, the very first data point is C transpose R minus 1, C minus 1, C transpose R minus 1. That is your very first data point. That's your very first common gain. Your maximum likelihood estimate, when you have two pieces of information, one that you predicted and one that you measured, is going to be C transpose R minus 1, C minus 1, C transpose R minus 1 times Y. Okay, so this, what you're doing is you're multiplying precisely the common gain by your observation. So you're saying my belief, my posterior belief, is my prior belief plus k of n times y minus y hat, where y hat, I have no prior belief. I don't know. I don't know what I'm going to measure. So I'm multiplying y by k, and that's going to become my posterior. And look, that's exactly what this equation is. So maximum likelihood is equivalent to having no prior beliefs. And that's effectively what that first data point is about. If you don't have any prior beliefs, it means that, x hat is, in this case, 0. Now, it may not be 0 for you, maybe some value, but if your uncertainty is infinite, then effectively you're doing maximum likelihood. But this gives us a recipe for computing uh, from beginning of this recursively all the way to the end of our estimation. Let me stop to see if you have questions. Yeah.
When this is used like practically, do people start with no priors or they like maybe do like 10 runs to generate it?
So these things are done in real time, right? So the question is, what should I start with? And of course the mean, okay, maybe the mean is 0. But the important point was about uncertainty. What is your uncertainty about the mean? And the difficulty was, if you really don't know anything, then that means your uncertainty is infinite, which means I can't use it. So, but now I showed you can use it, even if your uncertainty is infinite, by representing it in terms of how that infinity becomes something less in the next trial, P of 1 given 1, it won't be infinite. P of 1 given 1 is this. So then why not just start with that?
I think someone has a similar question last time, but for instance, if I want to start and here I have my C and R matrices, in reality, how do I find them if I want to do the accuracy?
I will show you. That's a different lecture. Yeah, so that's system identification. And the algorithm that you use is called expectation maximization. And so there you have to identify your system. So what I've been describing to you is based on the notion that you have an internal model of your system. So you have the A matrix, the B matrix, the C matrix, the noise in your state update equation, and the noise in your measurement. You know those things. And you just want to estimate the internal state. But the question of, well, how do you get those? That's system identification. And the algorithm is called expectation maximization. I'll teach you that. Right? So you have a model, you're making measurements, you want to combine what you predict using your model to what you observe. You want to combine those two things. Kalman filter is a way to do that. But it assumes you have a model. Okay. All right. So let me write the equations once more. I want to make sure we understand the procedure. So we have a model of how my system is going to evolve. I begin with a prior belief, x of 1 given 0, p of 1 given 0. I update my belief based on the common gain. What's y hat? What do I subtract my observation from?
Yeah.
C?
Excellent.
Right, is that clear? Why? What's going on? Okay, so that's how I update my belief. Okay, what is K? K is the relationship between my uncertainty about the knowledge that I have with respect to the noise in the measurements that I make. So how uncertain I am about what I know with respect to how uncertain I am about the measurement I make. What's the measurement noise? That's the variance of y. What's the variance of y given x? It is c times variance of x. What's my uncertainty about x? That's called p of n given n minus 1. C transpose plus variance of epsilon y, which is r inverse. That's k. Then I have my posterior uncertainty. And by the way, this k is the result of minimizing the trace of the posterior uncertainty, p of n given n. So if you take this equation, write its variance, then minimize the trace of that variance with respect to k, this is the result that you're going to get. And then if you put that k into the posterior uncertainty, the variance of the x hat of n given n, you're going to get an equation that looks like this. This is the posterior uncertainty for this system. Okay, so now this is the trial n. Now I'm going to move to the next trial, n plus 1. So I'm going to have a prior belief in trial n plus 1. So what is x hat of n plus 1 given n? What's my prior belief on trial n plus 1? Good. And what is that? Excellent. What's my uncertainty about that mean? So remember, beliefs are distributions. They have a mean, they have a variance, right? So we were representing knowledge probabilistically here. So when I say, what's your belief? You're giving me, in this case, a mean and a variance. The mean that you give me is this. This is what you believe. And the variance is going to be this. So what is the variance? What's the variance of the uncertainty that you have? What's the variance of x hat of n at time given n? It's a variance of this equation. This is the mean of this equation. This is going to be the variance of that equation. So the variance of that equation is a times variance of x, which is the prior uncertainty, times a transpose plus q. Right? From trial to trial, we build this system. Okay, so this process, as you will see, is intimately related to something called dynamic programming. So when we get to the Bellman equation, when we solve optimal control problems, you will see that whereas this recursive method is a forward in time, when we solve optimal control problems, the Bellman equation solves it recursively but backwards in time. It begins at the end and goes backwards. Here, we begin at the beginning and go forward. You will see how the two are highly linked to each other. Okay, so far so good. Any questions? Okay, so all the things that I've shown you so far has been based on Gaussian noise. Gaussian meaning that the variance of the noise did not depend on the mean. So the mean was 0 and the variance was, some value, right? Now, it's possible that the mean isn't 0. So in that case, noise will have some non-zero mean. But more interesting is the condition where the variance depends on the mean. So let me introduce that concept to you and then go and solve the problem for you. And this is called signal-dependent noise. So what does that mean? So suppose I give you a force transducer like this, and you put your finger on top of this force transducer, and I measure the force that you produce. And I tell you, produce 1 Newton of force. And so, you produce some force like this. This is time. And then I tell you to produce 2 Newtons of force. And it looks like this. And 3 Newtons of force. And it probably looks like this. Okay, so you notice that the variance grows with the mean, right? So in almost all real systems that I know of, variance is not independent of the mean. It depends on it. And in a special class of systems, which we're going to call signal dependent noise, what that means is that the noise depends on the mean, the signal, if you will. And for example, if I push harder, I also will have greater noise in the variable that I'm producing, in the force that I'm producing. So what does that mean? So suppose force is written as F is equal to U plus epsilon U. So U is the input that you give, force is the random variable that I'm measuring. And so in this case, what is happening is that epsilon U is some normal would mean 0, but its variance depends on U. So perhaps in a quadratic way. So what this is saying is that variance is growing as a function of U in this way. It's not independent of it. So that means the expected value of the force that you produce is the input that you give, but the variance of the force that you produce is, in this case, c squared u squared. So the greater input you're giving, the greater noise you're going to get. The variance is going to grow. This is called signal-dependent noise. Does that make sense? Okay, so we want to deal with systems like this and ask ourselves, how do we do it? So what if I write force, not just U plus epsilon U? What if I write it as U plus U times C times phi, where now phi is a normal with mean 0 and variance 1. So if I write it like this, what's the expected value of force? U. Because the expected value of the second term, the only random variable is this phi, which has mean 0. So far, so good, right? And what's the variance of this force? U squared C squared. Good. So this is equivalent. So if I write my equation this way, this is equivalent to this. And what I've done is that I've replaced my noise with something that is Gaussian and signal independent. Because the random variable now is something I can handle. I know how to handle those guys. It just gets multiplied by this guy UC in the front. Okay, so that's how we're going to handle these kinds of problems. So now let's go to the Kalman framework and deal with problems like this. But before I go, let's see if you have any questions about this. Okay, so let's write the problem now. So I have a system that looks like this. Where epsilon u is a normal with, well, let me write epsilon x first, the easy one. So epsilon x is my normal zero mean variance, zero mean Gaussian where the variance doesn't depend on the mean. And but I have some noise here, epsilon u, that's going to be dependent on u. And I have some measurement that is dependent on, let's call it h of x of n. And maybe my sensors, the things that are measuring this internal state, also have some, signal dependent noise. I'm going to call it epsilon s plus epsilon y. Okay, so what is this epsilon u? So epsilon u, since x is a vector, u is a vector, epsilon u is going to be a vector too, and it's going to be c1 u1 phi 1 to, let's say there's p of these guys. So u is a p-dimensional vector, py1 vector, and I'm going to represent the signal-dependent noise in it using this random variable phi, which has a mean 0 and variance 1. And epsilon s is also signal-dependent noise, which depends on this vector x. So I'm going to use the variable psi to represent, and maybe x is q-dimensional. So that's the noise in this. So the reason why I want to do this is because I'm going to have an actuator that's going to produce some force, but the force is going to produce is going to be signal dependent. It means that the harder you push it, the more variance is going to have. And you have some sensor that's measuring the internal state, but the larger the internal state, the greater the noise in what you measure. So maybe you're measuring light or something. The greater the intensity of the light, the more noise is going to be in your sensor. Maybe you are pushing on a motor, and the greater you push on it, the more noise is going to. That's the idea behind this, okay? And so we took epsilon u and we represented it as signal-dependent noise. Each one of the elements of this u can have independent noise, and we have this measurement that has also signal-dependent noise in it. Okay, so how do I proceed? The story is really quite simple, but it was solved. It was solved back when I was a grad student by I was a student, and my office mate Emil Todorov was the first person that I know of who solved this problem. He's a famous guy who made a software called Mojoko, which I don't know if you guys have heard about. It's a way to simulate dynamical systems. They use it for, any kind of simulation that you want to have, like things that are flying around and you want to have real physics. It's a physics engine. And so he's a probably a multimillionaire because I believe Google bought him out and they used this physics engine. But he solved this problem. And we're going to solve it also today, and it's going to take us about 10 minutes. So just goes to tell you, good thinking doesn't need to take forever. All right. So we have these noises here. How are we going to represent them? And the idea is to be able to represent these noises in a way that we can find their variances, because that's all we need to do, is to be able to find the variance of epsilon u and variance of epsilon s. And somehow we want to be able to do this. And the way to do it is to write this problem in a way that I can write it linearly. So I'm going to say that I'm going to be able to write epsilon u, which is a vector, as a sum of p vectors. And each of them is going to have this matrix Cu that's going to multiply by u times phi I. So what is the C going to have to look like? So C1 has to be something that's just going to have this element C1 in it, and then a bunch of zeros. And then this matrix C2 is going to have C2 in it, and then a bunch of zeros. So C1 and C2 are these guys, these gains here. They're going to become part of this. And so basically, instead of writing epsilon u as this just vector, let me write it as a sum of matrices, very sparse matrices, times the vector u times this random variable phi I. Similarly, for epsilon s, I'm going to do the same thing. So there's some transformation. And why am I doing this? Because I want to be able to find the variance of these guys. So now if I have this, then I can write the variance of what's the variance of epsilon u. That's the sum of I is equal to 1 to p times c, the variance of the sum of ci times u transpose times ci, because the variance of phi is just 1. Similarly, the variance of epsilon s So the idea is transforming your noises, which depend on the signal. Epsilon u depends on u. Epsilon s depends on x. And I'm going to be able, in order to write the common gain, I need to be able to find the variance of this equation, which means I have to find the variance of epsilon s. Well, look, I just found the variance of epsilon s. There it is. And in order for me to find my prior in one trial and how it transforms to the prior on the next trial, I need to know the variance of this, which means I need to have the variance of epsilon u. And look, I just found the variance of epsilon u. So, all right, so now the rest is easy. My posterior uncertainty is equal to my prior plus k times the difference between what I measure and what I believe. And what my belief is, what I predicted is the mean of this equation, which is h times x hat of n given n minus 1, because the mean of all the noises have mean 0. Similarly, so that's my how am I going to update my belief. So what's k of n? K of n is going to be the noise in my measurement with respect to my belief. So here's my prior belief times transpose of this matrix here, this guy here, that takes x to y, h, times the noise in my measurement. The noise in my measurement is h times the variance of this equation. So let me multiply that out. So this is going to be, maybe I can just write it out first. It says h times x plus h times epsilon s. So that's h times p of n given n minus 1 times h transpose. That's the variance of h times x. There's a transpose here. Plus the variance of h times epsilon s. So here's the variance of epsilon s. So that's h times this quantity h transpose plus the variance of my measurement noise, epsilon y, which we called r, I believe. This term, variance here. So I just wrote the variance of this, and I put it inside the parentheses, and I inverted it. So this looks just like what we had before. Here's the first term, here's the second term, but now I have this new term here, which is the signal-dependent noise associated with my sensor. Did I call it R? Yeah. Okay. So that's my Kalman gain, and then I have my posterior uncertainty, which is I minus K of N, H, P of N, N minus 1. Okay, so now trial N plus 1. I need to now know my prior on the next time point. Well, what's the expected value? What's the expected value of this equation? It is x hat of n plus 1 given n is a times x hat of n given n. That was my posterior plus b times u of n. And that's the expected value. I gave some input u. I had some state x hat of n given n. That's where I expect the system to go at time point n plus 1. What's my uncertainty at time point n plus 1? That is a times p of n given n, a transpose. Plus, now I have epsilon u. So now I have the variance here. I have this term here. So b of u doesn't have any variance, but b times epsilon u has a variance. So now I need the variance of epsilon u, which is here. So that's b times the sum transpose times b transpose plus q. That's the variance of the state update. And that's signal-dependent noise. So the trick was to be able to represent your noise in such a way that you could find its variance. And it's just, matrix algebra. And look, let's think about what does it mean. So let's see what just happened here. So what happened is that when I have signal-dependent noise, my uncertainty about the state in the future grows as the square of the inputs that I've given, which means if you gave a large input to the system, your mean grows as the mean of that input that you gave, but your uncertainty grows as the square. Look, the u is being squared here. So the greater input that you give, the more uncertain you are about where it's going to go, which should make sense, right? Because the noise grows with the input u. Your common gain, on the other hand, look, the common gain has uncertainty associated with the measurement you're making. And that measurement that you're making, the larger the value of x is, the more uncertain you are about that measurement. So if your sensor is measuring a large quantity, that means that your uncertainty is going to be larger than if it's measuring a small quantity. And so you will tend to not believe what you measure if the thing that you measure is a large quantity. If you're seeing a bright light, because the variance is greater in your measurement, you're not going to believe it as much as if it's measuring a small signal, because noise is signal dependent. That's what that means.
Apply all of this to like non-algebra.
Yeah. You just have to be able to represent its mean and its variance. Now, if it's not Gaussian, then the information content is not just in the mean and the variance. What's special about normal distributions is that you know everything when you know the mean and the variance. But if it's some other distribution, then that's not enough. But the idea of the Kalman filter is optimize your belief so that you minimize your uncertainty. And so you have to have some measure of uncertainty. In this case, it's the trace of the diagonal, the trace of the matrix, which is the sum of the diagonals. And if you think about what variance is if you have a two-dimensional system, x1 and x2. It's variance of x1, variance of x2, and then the covariances are just the off-diagonal terms. So if you minimize the sum of these two, you're also minimizing the off-diagonal terms because that's just a multiplication of them. If you minimize each of these guys. And so if you have a non-Gaussian, if you have some other noise system, the idea remains the same. You have to determine, you basically have to come up with a way to understand your uncertainty, some measure of uncertainty, and then minimize that at every time point. Typically, what's done is that if it's a nonlinear system, you linearize it around the X that you're in. So wherever region you're in, you assume a linearity. And if you are some other region, then that just means that your matrices A, B, and C are changing. It makes it so that those things become X dependent. That's what nonlinearity means. You just linearize it locally, and you apply the same equations. Okay. Wonderful. So next time I will delve more into using these equations to think about brain-machine interfaces and how they are applied. Thank you so much.